everyone. My name is Ricardo Palmafraga, and I'm an international student originally from Caracas, Venezuela, at the University of Oklahoma. I originally came to the university many years ago, and I pursued a bachelor's degree in industrial and systems engineering, which I liked so much that then I decided to stick around for a couple more years and pursue a master's within the same area, but emphasizing human factors, which I was able to finish in May, thankfully, even though we are going through a global pandemic, which I like so much my time here and as a grad student that I decided to stick around for a few more years to pursue a PhD emphasizing the interdisciplinary area of human factors, ergonomics, machine learning, and visual analytics. And before we get into the poster, I would like to give a quick shout outs to my advisor, Dr. Siho Khan, who I work with under the Human Factors and Simulation Laboratory at the University of Oklahoma. He's given me the opportunity to work in a lot of really cool projects related to air traffic control and human factors, and has given me also the opportunity to participate in the Center of Excellence for Technical Training in Human Performance of the FAA for quite a couple of years now, which has been a great experience. I would also like to thank the center as well for all the opportunities that they're giving us students in terms of competitions and networking opportunities with industry leaders, professors from other universities, and of course other students who are interested in this area just as much as we are. And now we're going to get into the poster. Alright, so in this poster titled Characterization of Air Traffic Controllers Visual Search Patterns and Control Strategies, led by Dr. Siho Kang, who was the PI, and Dr. John Dyer, who was the co-PI, as well as Stephen West, who works in the Air Traffic Management program here at the University of Oklahoma, myself, and three of my fellow graduate students, Aptarshi Mandal, Sarah McClung, and Kelvin Eku. So, the idea behind this research was to investigate what are the ways that expert en route air traffic controllers search the environment that they're working with, what information are they looking for, how do they capture that information, how do they process it, and how that leads them to identify possible conflicts in the environment. Once they have identified conflicts, if they exist, how do they solve them? How do they mitigate this kind of conflicts? The idea behind this research is that, as previous research by Dr. Khan has shown, is that novices, when shown this kind of information and this kind of patterns and search strategies of experts, they tend to want to mimic those behaviors, which reduces the number of errors they make and helps transition them from novices to experts much faster. The problem with this kind of information of talking about how do experts search and what are they looking for and so on is that it's kind of a bit of tacit knowledge. It's really hard to explain why are you looking the way you're looking, especially because that skill set is built throughout many years of experience, a lot of training, so it's hard to just boil it down and explain it with words. So in this experiment, what we did was, with using a lot of expert en route air traffic controllers and an eye tracker device from Tthp, we were able to explore how do veterans apply visual search scanning procedures and how are they different from each other, what are the similarities between them, what information are they looking at when they're scanning, where do their scanning start, after they're done scanning, they identified a conflict. How do they know which conflict mitigation strategy they want to apply? Do they want to change altitude? Are they going to change directions of the aircraft? Which aircraft are they going to change? And so on. You try to get an understanding of how do veterans air traffic controllers apply these strategies, what heuristics do they use. So for this experiment, we used 11 veteran air traffic control specialists, and we used a simple to complex high fidelity scenarios in a high fidelity simulation where the veterans had to identify and mitigate conflicts if needed. There were a lot of conflicts present. Some scenarios had conflicts that were present, some scenarios had different types of conflicts. You could have aircraft that were tailgating, that were in a converging situation, which at some point, unless an action is taken, they could possibly crash. There's scenarios where many aircraft were in one particular area of the screen in order to see if do veterans suffer from like tunneling vision, where they only focus on that particular area of the radar or the environment, but they tend to ignore other areas and so on. And throughout all of these scenarios, their eye movement data was recorded, as well as multiple post-scenario interviews were held with the participants in which they answered a lot of like standardized questions from a survey that we designed. So that is the motivation behind this project and why it's important. So the results show that there are many the veterans when they're scanning when they're scanning the environment, they tend to make a lot of movements on. They think that they've identified a conflict. If they're scanning the environment and they identify a possible conflict between two aircraft, they tend to scan multiple times around those aircraft to confirm information of what they've seen. So you can see that in figures A and B here on the right side. The yellow circles denote the aircraft of interest near the conflict, and the red arrows show how they keep moving between those two aircraft to confirm that, oh yes, these aircraft are actually in conflict. Then in figure C and D, there's representative examples of the type of ways that veterans tend to visually scan the area. So in this case, we see that, for example, some of the geometrical patterns that we saw were circular, linear, spiral, or mixed. And mixed is just a combination of any of these other geometrical patterns. Here, figures C and D showcase examples of a circular pattern and a mixed case pattern. This might not exactly look like a circle, but it follows that same pattern, that it's just one connected line that starts at one point and goes through the entire environment until it reaches the final aircraft. Of course, it's not exactly like a perfect circle because it depends entirely on the location of all of these aircraft. And then lastly, on the results section, we have participants' responses throughout the interviews were quantified. So this is an example of one of the questions that we were asking participants. If they could describe their visual search strategy in a geometrical pattern, what pattern would it be? So a lot of participants said spiral, some said circular, some said linear, and there were others because, again, it's hard to explain how, if you're using a particular pattern when you're scanning, some said that it was random. But other questions that were interesting were, for example, where do they start scanning when they get to the radar? Do they start scanning at the middle of the screen? Do they start scanning in a particular group of aircraft? Do they start at the bottom of the screen and then move up? Or where do they start? So a lot of participants say that there's a bit of a consensus on that they start in the high density areas for safety reasons, because in those areas, if there's a possible conflict, there's not enough time, there may not be a lot of time to make an action to mitigate that conflict. And then we were able to map some of these geometrical patterns to actual visual search scanning patterns that we recorded from the eye tracking data. And from this, our conclusions are that we were able to categorize visual scanning patterns into these geometrical patterns. And in addition, we were able to identify several hierarchical heuristics that veterans utilize to identify conflicts. For example, when veterans are scanning the environment, they're gathering information in a particular order. Mainly, they're looking at altitude, followed by the direction of the aircraft, and lastly, the speed. Which makes sense, because if two aircraft are at different altitudes, then there's no way they're going to be in conflict. If they're at the same altitude, depending on the directions, they could be in conflict. And if all of those two match, then depending on the speed, there could be a potential conflict. As well, we identified several hierarchical heuristics in terms of mitigating conflicts. So, for example, changing altitudes will tend to resolve most conflicts, but sometimes that's not ideal. Sometimes you want to increase the customer service that controllers provide to this aircraft by changing direction and putting them in a favorable tailwind to make that aircraft go faster. As well as some of the environmental factors such as weather conditions can affect these hierarchical heuristics that we were able to identify. And yeah, that's my poster. Feel free to go over it. I just kind of went over like the brief general area of what the poster's about, but if you guys have any questions, feel free to reach to either myself or Dr. Kang. Thank you guys.